Welcome to week 6 of the artificial intelligence stream of KF5012. This week we are going to be looking at some advanced deep learning. So we are going to look at some of the really popular architectures, and then we're going to look at transfer learning. So how you can use the popular architectures within your own projects. Then we're going to look at ethics, bias, and interpretability. Following that, we're going to look at some of the really cool things that are up and coming in AI, like generative models and transformers. First, I'm going to take a quick look at Inception. Inception's an old network at this stage, but it's one of the early ones, and it just shows you some of the creativity that you can have when it comes to building a neural network or a convolutional neural network. So with Inception, if you have an image that's whatever size, usually when you're doing a convolution, you just have this kernel which is 3 by 3, and you move across and then you move down a little bit and move across. You have this sliding window that we've seen already. With Inception network, you have something a little bit more. So this 3 by 3 convolution is gonna only be one path through each layer. So this is what's going to happen at every single layer. But you're also going to have some additional kernel sizes. So rather than just choosing one kernel size, we're going to play with multiple kernel sizes at the same time. So you might have a 1 by 1 kernel, which is going to be in this path. Or you might have a 5 by 5 kernel, which is going to be in this path. And then we've also seen max pooling, which they do as well. And then, these 5 by 5 and 1 by 1 convolutions are doing the exact same thing. They're going to go across and then down and then across again, doing the exact same thing, but it's just a slightly different kernel size. Finally, we have this concatenation. So there's lots of different ways that you can concatenate stuff. Often we'll see with a vector, you'll have vector 1 and vector 2, and then just concatenating them means you move vector 2 right next to vector 1 and just make this a longer vector. In this case, we're going to be concatenating them in the channel dimension. So this you have an output channel for the 5 by 5, which is going to look like that. You just need to make sure that everything is the same size essentially. So then you'll have an output channel for the 3 by 3, and then an output channel for the 1 by 1 as well, and then a channel for the max pooling. And then you do this multiple times and you get multiple more channels, each with different kernels for the 1 by 1s, and different 3 by 3 kernels, different 5 by 5 kernels. That's a slightly naive way. A bit more advanced is to use these 1 by 1 convolutions just to change the size of the feature maps. This just helps you make sure that you get these outputs all to be the same size, so that your concatenation is nice and simple. You don't really need to worry too much about this if you don't understand it so well. This is just an example of how creative you can be when you're designing your networks. It doesn't have to just be a boring layer followed by another layer, followed by another layer, followed by another layer. Okay, so on that note, let's start talking about ResNet. So, I asked you this question in the last lecture: is this an example of overfitting? And the answer is no, because this is all still training error. So as this has got deeper, we get a higher training error. But overfitting, remember, is when the training loss goes down, but the error on the test set actually goes up. So in this case, because we don't know anything about the test set, we can't conclusively say that this is overfitting. but we can say that something is going wrong. And ResNet is going to be the one ResNet was the first paper or the first architecture that could solve this problem. So it's this paper in the bottom left, deep residual learning. What's happening with this really, really deep 56-layer convolutional network, if we're not using residuals, is you get something that's called a loss landscape that looks like this. So remember, we talked a little bit about gradient descent, where you have some sort of loss function and you want to find the minimum point, and you'll have this and you'll compute, you might be here, then you'll compute a gradient and that'll tell you which direction you need to go, and you want to end up at the bottom. The problem when you have some loss landscape like this is you might get caught in one of these local minima. So instead of having a nice graph like this, instead you might have something like that, and you want to get to here, but if you're stuck here, then you might even try getting back up here, but then the gradient is going to point you back in that direction, so you're going to get stuck in this local minima rather than going to a global minima. And sometimes these are actually multi-dimensional wormholes as well, which is really difficult to get your head around, so don't worry too much about that, but hopefully you can see that it's difficult to find a path to get all the way down to this local minima. But this was solved by ResNet. So what is ResNet? ResNet is saying if you have your regular 56-dimensional or 56-layer convolutional neural network, you should actually be able to get just as good results as a 20-dimensional network. So let's imagine that this is your first 20 layers and then these are your next 36. Once you get to H20, so your hidden representation at the 20th layer, you should be able to get to H21. If you just say that H21 is equal to H20, then for the next step you'd say H22 is equal to H21 and do that all the way. So essentially you don't change anything until you get to this output layer. If you don't change anything, then you should get the exact same results as you do at H20. So what they've done with this ResNet is actually force this mapping from Hn to Hn plus 1 to be almost identical. And this is called the identity mapping. Right, so in maths, the identity function is something that is going to map an input to itself. So if you think about addition, then the identity function is going to be 0, because if you do any number n, plus 0 is going to be n. When we're talking about multiplication, the identity function is going to be 1 for the exact same reason. So in this case, they actually just send this x through to the end and add it to whatever gets computed by the network. So this is your regular neural net, your regular layers, but you're just doing what's called a skip connection, which means that you're adding this additional x to your output. And personally, I find it more intuitive to think about it not in this stage, not in this way, but instead to think of it more like this. So you have your input, which is just going to be from your layer, and then your output is going to be exactly the same. So you're just sending x to itself, and nothing has changed there. But now we have this additional path, which is going to do some computations, and that is going to work out what differences you need to get a slightly better representation here. So now you're not going for a completely different, new, deeper, more complex representation. You're just adding this additional path and doing this addition to work out what needs to change from this representation to this representation, rather than completing something completely new. For a 34 layer ResNet, this is what this looks like, and the difference from a simple 34 layer ResNet, they're just showing that these are exactly the same except for these skip connections. So this is the only thing that changes. And you can see when they test the error, so the thick lines here are going to be the test errors and the thin lines are training errors. So this is where we can see that there is some overfitting. Almost always there's going to be some overfitting with deep networks. But you can see the 20 layer model is in this yellow, and then the 32 layer is in cyan, 44 in green, 56 in red. With the plain CNNs, when you're not using these skip connections, you get worse and worse results both on test and on training. However, the opposite is true when you use residuals or when you use skip connections. So now they have this ResNet 20, 32, 44, 56, and even 110. And you can see in all these cases that the deeper the network gets, the lower the training error, and also the deeper you get, the lower the test error. So this just shows how much better their performance is, that now this actually allows for the first time for us to consider some of these very, very deep networks. So how far can this go? Well, they tried to use a convolutional neural network with these residuals with 1,202 layers. And it turns out that that's too far. So there's still an element of what was going on before with the gradient descent where it can only find a worse solution. But you can see that even the fact that we get to 110 layers is already a massive improvement. And this is just to show you the equivalent when we talk about the loss landscape for ResNets. So this is what we had before, which is horrible and irregular, and you've got loads of these wormholes and places that you can get lost. Whereas the ResNet loss landscape is very nice and easy, and you can just very easily slide your way down into this local minima. Last thing I want to talk about for this lecture is ImageNet. So ImageNet we've discussed a little bit, very slightly before. ImageNet is just a massive, massive, massive data set with loads and loads of different classes. This is essentially the biggest image categorization net that is widely and publicly used. The problem is that in the past we have talked about generalizing to new data sets, and hopefully you remember from before my very beautiful drawing where we have this red line, and this is the distribution that we train on. If we get a new distribution like the green line, which is still doing something very similar, but it's just got different people involved, or it's images taken at a different time of day or something like that, then the model can struggle to generalize to this new source. So for example, this is why Alexa struggles to understand your Geordie accents. So what can we do now if we have something that's massive, that's got many, many thousands of classes like ImageNet, that could just represent like to a realistic degree, like almost everything that we regularly see in this world, how can we actually make use of these massive data sets when we have this problem when it comes to generalizing to new data sources? Pause the video, have a think, and try and work out what you would do. Right, so hopefully you've had a think, and this is the solution, which is that you would first train your CNN on ImageNet, and then once you have that trained CNN, you have all of the features that are optimized for all of these different categories. Once you have that, then you can actually do what's called fine-tuning. So this stage here is called pre-training, and then you have fine-tuning, where you take that CNN, you take this trained CNN on ImageNet, and then you apply it to your data. So what's happening here? Let's imagine that we have a task where we're trying to categorize people. And you've got this very, very big network, which is trained on ImageNet. Well, you're going to have loads of features that aren't going to actually be relevant to your data. So all of these features that are regarding like aeroplanes over here, and then you've got boats in this section, and you've got all sorts of stuff. You've got like, I don't know, is that kitchens and stuff down here, and TVs and stuff like that. All of these are completely useless. So what you're doing when you do this fine-tuning is you're trying to take this model that's been trained on ImageNet and teach it which of those features that are very complex and very expressive, which of those features are going to be most useful for your data. So if you're doing something about people, maybe all of the features that regard people are just in this sliver of your layers. And in that case, all the weights that are going to be in the rest of the kernels are not going to be useful. So you can set them to something like 0 and just make decisions on this part of the model. So ImageNet is massive, and we've talked in the past about this current state of the art on ImageNet taking 2,700 hours to train or something ridiculous. What do you really have to train your model on this and wait for that long, so just so you can fine-tune it on your data? And the answer is obviously no. So what people do is when they release this big models that are trying to beat the state of the art, they actually release the models that they've trained, and all you have to do is take those models with the weights that they have trained, and then you just have to worry about this bit. So there are certain things that you can do to make your models better, specifically for your data, but you don't need to worry about this whole first stage. You just take the models from the net with all of their weights trained, and then just do this final stage. So that's going to be everything for this video. I will see you in the next one.